So, we have seen that this, if we apply magnetic field on a magnetic material, so we can get some parameter. So, that is magnetization as a function of magnetic field, right. So, one should measure the magnetization of that material as a function of magnetic field. Okay. And one can find out then chi one can find out, and then mu one can find out permeability. The relation I have shown you, what the relation B equal to mu 0 mu r h, right, and then from here I have shown that these have two contribution. One is this, another is from magnetic material, this is magnetization, right, and where m is basically what we got, this mu r minus 1 into h, right. So, then chi equal to m by h, that is the mu r minus 1. So, if I measure the magnetization as a function of magnetic field, right, as a function of magnetic field, so I can find out chi, right, m by h. If I find out chi, so you will get the permeability of this material. So, if I get the permeability of the material, so then I can see the value whether it is less than 1, then I will tell it is the diamagnetic material, or then I will see whether it is greater than 1. If it is slightly greater than 1, then I will tell it is paramagnetic material. If I see this is a very greater than 1, then I will tell it is ferromagnetic material. So, in ferromagnetic material there are other categories, antiferromagnetic, ferrimagnetic. Okay. So, these without knowing the details, one can study the magnetic material experimentally, just measure magnetization as a function of magnetic field. So, but as I mentioned that the origin of this property comes from the atomic contribution. Okay. So, this basically induced dipole moment as well as permanent dipole moment, right. So, now how, so this as I mentioned that this material should have either induced dipole moment or permanent dipole moment. So, induced dipole moment, it comes when you apply magnetic field, then this induced dipole moment occurs. But permanent dipole moment, it is nothing to do with the magnetic field, this material itself, it have this some dipole moment exists in the material. Okay. So, then we tell this a permanent dipole moment. The material does not have dipole moment, but if we apply magnetic field, then this magnetic field induced dipole moment in the material, then that is the we tell the induced magnetic moment. So, this present in presence of magnetic field, this present in absence of magnetic field. Okay. Now, when we apply magnetic field, so in this case this induced dipole moment will occur, that is fine, but for other case this magnetic property is decided how this permanent dipole moment are oriented towards the magnetic field. Okay. So, depending on that tendency of orientation of this permanent dipole moment towards the magnetic field, so that will decide the magnetic behavior of that material, whether it is paramagnetic kind of material or this other ferromagnetic kind of material. Okay. So, these are the, so to understand the magnetic property of a material, so these are the basically macroscopic point of view one can define a magnetic material this way, but this macroscopic that property comes from this microscopic property. So, microscopic, so it is atomic level. So, one has to understand, one has to look at the material from the microscopic point of view, right. So, if you take microscopy and see the material, what you will see? You will see the atoms sitting in the material, atoms sitting in the material, right. So, now I am discussing about the origin of the permanent dipole moment, So, if I take a material, see in this material, so there will be atoms sitting at the lattice point, say, or we will see the lattice point. Okay. Atoms are associated with this lattice point, as we have seen from crystal structures, right. As we have seen from the crystal structure, right. Now, say these are all this, they are atoms arranged in the material. So, if I apply magnetic field, so this atom responds to this magnetic field, this atom responds to the magnetic field, how it responds there. So, let us take just one atom. So, let us see how this permanent dipole moment coming in this material. Okay. So, definitely this comes from this atom. So, let us see this atom. In atom what is there? If you take this atom, in atom what is there? Already I have discussed earlier. So, it has nucleus and then electrons are on orbit, etc. right. So, put you know how many will be there, etc. that you know, just I have put arbitrarily. So, atoms is having nucleus and then it is having the electrons in orbit, right. So, electrons in orbit, so let us take one electron, just pick up one electron which is rotating in orbit, one electrons, okay, which is rotating in orbit. Okay. So, as you know, this when electrons have negative charge, it is rotating in a closed path. So, it will give current, and current in a closed path, it will give you magnetic moment, right. So, due to orbital motion of the electron, okay. So, this So, this will give magnetic moment. So, this magnetic moment for this orbital electron, if it is mu, again I am writing mu, see this mu is dipole moment, it is not the permeability. So, mu I am writing this is for electron, this is for electron and that for orbital motion L. Orbital motion, it has angular momentum L. So, I am writing this magnetic moment for orbital motion. So, mu E L, right. So, mu E L, so that is I A current in this closed loop and the area of the closed loop, and then I is omega by 2 pi, omega by 2 pi is nu, means in 1 second this electron will nu times it will rotate. Okay. So, charge it will pass through a point nu times, right. If charge is E, so total charge pass through this one point on a orbit, it is E nu, nu is omega by 2 pi, nu is omega by 2 pi. So, if you multiply with E, so this amount of charge will flow through a point on the orbit per second. So, that is the current and area is pi r square, area is pi r square if it is r, orbit radius is r, right. So, this is giving me, and this charge is, electron charge is negative. So, I will put negative sign, So, that is minus omega E omega r square by 2. Okay. So, that will be the magnetic moment, orbital magnetic moment of the one electron, right. So, we have many electrons in a atom and they are in different orbit. Okay. They are in different orbit. So, here this r will take care of that different orbit. Okay. So, this is the one relation, just let me keep it here, mu E L equal to minus E omega r square by 2, E omega r square by 2. Okay. Now, as you know this angular momentum, so this electron are moving, so it has angular momentum. What is the angular momentum? Angular momentum mvr, right. V is velocity, right. So, this L angular momentum L mvr, it is m, V is basically omega r, so omega r square, m omega r square, angular momentum is m omega r square, right. So, if I take the ratio of this mu L by L, orbital angular momentum, orbital magnetic moment or angular magnetic moment, orbital magnetic moment or angular magnetic moment, mu L angular magnetic moment, okay. If I take this ratio and this L angular momentum L, this ratio will give you minus E by 2m, right, omega r square will go. So, minus E by 2m, right. So this ratio is constant, you see, E by 2m, there is the electronic charge and this is the mass of the electron. So these are constant, and this called we write, say sometimes we use gamma. So this gamma is called the gyromagnetic ratio, is called the gyromagnetic ratio, or it is called also magnetomechanical effect, magnetochemical is effect or factor, or constant, this type of name is given, this one. So this is the important ratio, okay, and this is a constant, for electron in orbit. So what I got basically mu L by L equal to minus E by 2m, right. So this is the connection with the angular momentum and the corresponding magnetic moment, dipole moment, okay. So L, angular momentum, L is, so I can write in terms of L. So mu angular momentum L, it's what is the, so this angular momentum, it's we write, this is the vector, and it's we write L h cross, its value. So in this case L h cross, this L is called the angular quantum number, and its momentum is L times h cross in unit of h cross. Momentum is in unit of h cross. Okay. So L value can take 0, 1, 2, 3 up to n minus 1. What is n? N is the principal quantum number. Okay. So this we can write magnetic moment also vector, and this L angular momentum, that also vector. So this negative sign is telling that direction of angular momentum and corresponding magnetic moment, angular magnetic moment, they are in opposite direction. So that is the significance of this negative sign. Okay. So for different orbit, L are different, and then you will get different magnetic moment. So this I can write mu L is magnitude, is minus E by 2m L h cross. Okay. So then if I take h cross here, so it's like this, right. and then it's the I can write this its magnitude. I have written magnitude. So, forget this sign. Okay. So, then it is giving me L, this again this E h cos by 2 m again is constant, is constant for a electron. Okay. And this we write mu b, where mu b equal to E h cos by 2 m. So, this mu b is called Bohr magneton, Bohr magneton. Okay. So, we are dealing with this one atom, right, and in one atom what is the how this magnetic moment are coming. So, this lattice we will put these atoms in this lattice and then see the effect, overall effect from the material. So, that will come later. So, these are called Bohr magneton, Bohr magneton, since it is constant, right. So, its value is 9.27 most probably yes into 10 to the power minus 24, this very small value is ampere meter square. Okay. So, that is the in SI unit, this is the SI unit, current per meter square, right, current per meter, because IA mu equal to IA current and that area meter square. Okay. So, now this electronic charge it is expressed in terms of E unit, right. Similarly, this moment, magnetic moment, it can be expressed in terms of in unit of mu b, Bohr magneton, in units of Bohr magneton, right. So, now for different orbit we can easily find out for L equal to 0, for L equal to 0, this is the s orbital. Okay. So, what will be the magnetic moment? It is 0, its mu will be 0, right, L equal to 0. Okay. So, mu will be equal to mu b for p electron, p orbitals, right, for p orbitals, and then mu equal to will be 2 mu v for d electron, right. So, electrons in an atom are in different orbital, okay, wherever it is. So, it will give different magnetic moment in terms of mu v, So, we can find out. So, we can find out, right. Then, so this is the one source of magnetic moment in magnetic material, right, which is coming from the orbital motion of electrons, right. Second, okay. So, I think I can tell you that this is from one electron. Okay. So, if atom is having many electrons, so then following the Pauli exclusion principle, we can arrange them in the different orbitals, right. So, to find out the resultant orbital magnetic moment, so we have to sum take summation of this individual one, right. So, that basically we get from the vector model vector summation, right. So, instead of just adding this magnetic moment, one can find out the resultant angular momentum for this atom, okay, coming from these different electrons in different orbit. So, this L, total L, resultant L, it's basically L1 plus L2 plus L3, etc. Okay. So, that will give the total angular momentum of this atom, right. So, then it follows the same similar things. So, then mu E coming from this angular momentum, so that will be minus E by 2m, okay, L H cross. So, H cross is there. So, basically let me just, so that will be equal to L capital L mu b, okay, capital L mu b. So, one has to find out this resultant angular momentum L, right, and this L, as I mentioned, that one can get from the vector model taking the sum of them. So, if we just take 2 L 1, so L 1 equal to say 1 and L 2 is say 1, means both are p electron, okay. Then what will be the resultant L? What will be the resultant L? So, resultant L will be basically that we take L. So, from vectorial sum it comes L 1 plus L 2 to L 1 minus L 2. Okay. So, L 1 plus L 2 it is 2, So, it will L 1 minus L 2 is 0. So, it will go, it will have this L value will have 2 1 0. Okay. So, resultant L it can have 2, it can have 1, it can have 0. Okay. So, there are 3 possibilities, and which one it will take, that depends on the state of this atom, whether it is in ground state or whether it is in excited state, etc. But it can have only these 3 value. So, which value will be for this particular state of this atom. So, that will be decided depending on the state of this atom, whether it is in ground state or excited state, etc. Okay. So, whatever relation for one atom we have used, one electron we have used. So, just it is this relation are valid for this total, for this atom also, where we will get the resultant angular momentum. Secondly, or second contribution in magnetic moment is the spin magnetic moment. So, you know this electron have the spin angular momentum, right. Electron have the spin angular momentum, right, spinning motion of the electron, okay, about its own axis. So, it will also give this similar relation. So, magnetic moment, due to this magnetic moment of electron spin mu E s. So, divide by s. So, it is also minus E by 2 m. Okay. It also follows this same. Okay. And so, mu E s here s. Okay. Let me write small s. Yes. So, this is also angular, this spin angular momentum. So, it has magnitude s h cross, s h cross, s L can take, as I showed this value, s can take half, s can take only half of a electron, right. So, here one factor is multiplied, that is one factor is multiplied. So, that is G s, it is called G s, it is called, this factor is called Landé-G factor. Landé-G factor, the G is called Landé-G factor, Landé-G factor. Or it is called splitting factor, magnetic splitting factor, magnetic or magnetic splitting factor. Splitting factor. Magnetic splitting factor. It is called magnetic splitting factor because under, if you apply magnetic field, then this, before applying magnetic field the energy level was degenerate, after applying magnetic field it is splitted, Zeeman splitting. Okay. So, this splitting, this magnitude depends on this factor, magnitude, the splitting, this separation, it depends on this factor. So, that is called, that is why it is called splitting factor. Okay. So, for electron in a orbit and that has spinning motion. So, this G factor for this, for a spinning motion of electron, its value is generally 2.00024 kind of things, okay, or 0024. So, approximately this is taken as 2, okay, this is taken as 2. So, this is always 2 and this E h cross, again this is mu v, E h cross mu v. So, this we are getting G s mu v and s. For electron spin, that is s is half, this is half, all the time it is half for a electron, and this all the time this for G is taken for the electron spin, it is 2. So, it is basically mu v. So, from each electron, this magnetic moment of each electron, magnetic moment for spin magnetic moment, or this magnetic moment due to the spinning motion of the electron, it is mu v. Okay. So, each spin will give mu v value, magnetic moment will be mu v. Okay. So, mu E s, then mu E s is I can write the mu E s is mu v. Okay. So, from spinning motion of the electron we are getting the magnetic moment, this that is mu v. From orbital motion of the electron we are getting L mu v. So, wherever the L, it does not matter, for each case spinning, due to spinning motion of the electron we will get mu v. So, mu v is associated with the spinning motion of a electron, whereas angular momentum varies, depends on the angular magnetic moment varies, depends on the orbital, okay, and it is independent of orbital. Okay. So, this is the another contribution of magnetic moment in a atom, and that means in the material. So, third contribution comes from this nucleus. So, nuclear spin, and in similar way. So, the nuclear spinning motion, it comes. So, this if you write mu n s spinning motion of the nucleus. Okay. So, that again it is E by 2 m. So, now I am writing the m p, E by 2 m, m p, p is the mass of proton, p is the mass of proton. So, I will get this this is the ratio, this will be the ratio spinning motion of this will be the ratio of the nucleus, right. So, here whatever I will get, so this S is not, I think I should write spinning motion of the nucleus, So, this whatever m, that in case of electron, that is replaced by this proton mass, and this, and due to this magnetic moment, this what of the magnetic moment. So, this is called, similar to Bohr magneton, it is called nuclear magneton. This is called nuclear magneton. Okay, nuclear magneton, and that value, that is mu ns, and that value E h cross by mu phi. So, it is this I am writing mu. So, for magnitude again I am just this minus, it comes for direction. So, this we write mu n. Okay. So, mu n value, you see its value is 5.05 into 10 to the power minus 27 ampere meters. Okay. So, this the magnetic moment comes from the nucleus. So, atom has nucleus and electrons. So, electrons have two contribution, orbital and this spin. Magnetic nuclear have this due to spinning motion of the nucleus or nucleons. Okay. So, it will contribute. So, this contribution is mu v and mu n, mu v and mu n. Okay. It's more or less this factor is 3. Okay. So, mu b is 1000 times higher than this mu n. So, mu n nuclear contribution, angular this magnetic moment from nuclear contribution is very small compared to the electron contribution. Okay. So, that is why generally we neglect this nuclear contribution. So, overall what we saw, that magnetic moment, contribution in magnetic moment for a atom, it is coming from orbital motion of the electron, spinning motion of the electron and spinning motion of nucleus. Okay. So, as a whole, this all these three together, it gives a moment of the atom, So, that is mu. Okay. So, it comes from mu L for total all electrons, angular momentum, and it comes from mu s, capital S, because each electron is having having mu v, and just I cannot take sum of them because they are vectors, it has direction. So, magnitude I cannot sum. So, vectorial summation we have take. So, S is similarly for L, whatever the way we have taken, S will be S 1 plus S 2 plus S 3. So, using vectorial model one has to find out S, okay, and then this that. This will be the spin angular spin magnetic moment, and then other one is mu n. Okay. So, for all whole nucleons, so one will get n. Okay. So, but these are very, as I mentioned, this very small value compared to this other. So, one can neglect this part. So, mainly in magnetism, okay, the contribution is coming from these two. So, this is the mu, we can tell that this magnetic moment of this atom. Now, magnetic moment of this atom, it can come, it can be written also like mu j, it can be written as a mu j. Okay. So, j is the total, So, again j is the total magnetic moment, So, this is the Ls coupling, it comes from Ls coupling. So, it is again L plus S, j equal to L plus S, vectorial sum one has to take. So, again the j can take value, L plus S to L minus S, right. Okay. And you will get this mu j for this total angular momentum in same way. Okay. So, g, this Landry factor Gj j mu v. Okay. Gj j mu v. Okay. Here this factor is not there. So, sometimes we write here GL, sometimes we write GL. So, GL is 1, basically this is 1. In case of mu s, you write GS. So, that value is 2. Similarly, that Gj. So, Gj value one can find out, So, Gj value is basically 1 plus j plus 1 plus s plus 1 minus L, I think I should write here minus L plus 1 divided by 2j plus 1. Okay. So, that is the Gj value, Okay. So, thus you can get the magnetic moment due to angular momentum, due to orbital, angular momentum again 2 kinds, 3 kinds, this orbital angular momentum, spin angular momentum and total angular momentum. So, this contribution also it comes as a mu j. Okay. So, this is the total. Now, this value depends on this coupling, Ls coupling. So, now this is the atomic situation, magnetic moment for a atom, So, when this atom is put in a material, in a lattice, okay, so its situation is different. So, whatever this atom is showing the magnetic moment as a isolated one, when it is put in material, its magnetic moment it can be different, and most of the cases it become different. Okay. So, if outside for a atom its total magnetic moment, if we are getting mu j, but inside the material it may not show the moment mu j, it may show mu l, only mu l or only mu s. Okay. So, that depends. So, that depends on the this is the effect of the surrounding of the other atoms in the material. Okay. Influence of the other atoms in the material. Okay. So, that we will discuss whenever it is necessary, but right now we will take that this magnetic moment of this atom in solid in material is mu. So, this mu can be this mu l, mu s, mu j, that let us forget it. So, in a material each atom have the magnetic moment mu. Okay. So, then we will discuss the different properties, diamagnetic properties, paramagnetic properties, ferromagnetic properties in coming classes. Okay. So, let me stop here. Thank you for your attention.